Simcision can be used to model flows and derived states. Let's jump in and build a simple model to look at the core functionalities. Let's create a really simple model of a spoon factory. Let's say we have a metal warehouse where we store our main resource to build spoons. I'd create a resource element for that. Click on the resource button and on a free space anywhere on the canvas. Resource elements are great for concrete values that are clearly measurable. I know that there's exactly 1000 kilograms of metal in my warehouse. We can set the unit of the element, in this case I'm measuring kilos of metal, and we can set the capacity of the element. The warehouse can't go into negative numbers, and it has a maximum capacity of 1000 kilos. And we're not starting with an empty warehouse. Let's give it a starting value. Next, create the resource for our end product, the spoons. Make sure to give this element enough capacity too. Now, let's connect the two elements with a flow. That's the spoon production. Select our source element, the metal warehouse, choose the flow button, and select the end element. Now, we're connecting the source element with a sink element. If the selection is correct, click on Create Flow. Now we have a flow set up between the two resources. It doesn't do anything yet though. It needs a strength that defines how many resources to shift around. Let's start with a flow strength of 250 for now. As you can see in the canvas, the flow is now active. We switched from a dashed to a solid line. Let's switch tabs and look at our model in the simulation. Simcision has many different tabs that each contain helpful tools to interact with your model or analyze its dynamics. I'll go over those in different videos. In the simulation tab we can simulate our model and see what happens with it over time. Create a free simulation for now and start it. In Simcision, the simulation pauses at the beginning of each time step to give you the chance to interact with your models and change values manually. But for now, let's just see how the simulation plays out without interventions. Click on Simulate to advance the simulation by a time step. At the end of each time step, the flow is activated. The flow reduces the value of a source element by the flow strength and increases the value of a sink element by the flow strength. Afterwards, everything is added up and we move on to the next time step. Repeat this a few times and we quickly run out of metal in the warehouse. As soon as there's not enough left in the source, the flow strength is reduced automatically to stay inside the limit. As it's empty now, the flow completely dried up and nothing moves anymore. This auto-limiting is built into all flows and works in both ways. If a spoon warehouse was full, the flow would be reduced too. Let's move back to the model to add more different types of flows. The warehouse could be filled up regularly when a metal delivery arrives. That's also possible with a flow. Select the metal warehouse element, create a flow, and choose the inbound outside flow. This flow is not connected to another element, but it only influences the warehouse directly. This can be our delivery. The delivery brings in 1000 kilos of metal. It won't arrive in every time step though. The delivery only comes around every 5 steps. So we set up the interval to 5. Let's simulate this. In step 1, the delivery flow would be active, but the metal warehouse is full, so it won't bring in anything. Let's go on. In round 5, the flow activates again and delivers 1000 kilos as planned. That's the delivery done. We can add in sales of spoons the same way. Select the spoon resource, add an outgoing flow to the outer system limits, and set up a flow strength. Let's say we sell 100 spoons every round. Short intermission. We're currently still using rounds as a time unit in this model. To ground this model in reality, let's change this unit. For this, open up the system context and choose the time unit the simulation should be set in. You can also define the simulation length and the main topic of your model here. Let's return to the model. There's one thing that's not right here yet. 1 kilo of metal does not only produce 1 spoon. You'd surely get at least 30 spoons out of every kilo. So let's adjust our flow to consider that. When editing the flow, you have a source and sink here. Here we can set a factor for our sink flow. For 250 kilos of metal, we'll produce 30 times that amount in spoons. That's more realistic. Let's adjust our element limits to the new amount, and the outbound flow too. Great! Let's do one more thing. Forging a spoon might need more than just metal. We might need energy too. Let's add in an element for the amount of available energy. Melting a kilo of steel takes around 1 megajoule, so let's just take that as the energy requirement, and let's assume that we have a maximum capacity of 2 megajoule in total. We can now add in the energy to our flow. To produce spoons, we have to take energy away, so we'll include the energy in the sources. Let's adjust the amount of energy taken too. Our base flow strength is 250, so we have to set our factor to 0.004. We could also go the other way around and change our flow strength to 1 and adjust the factors for the metal and spoons. That might be even easier. Let's do that. Now, that is readable. Let's simulate that. As you can see, the flow now always takes from all resource elements set as sources. But when we reach day 3, the energy is used up, so production halts. The flow only works when there's enough resources in every source. Now, one last thing. Let's prevent the energy from running out. For this, we will refill the missing energy each day. To be really accurate, let's calculate the energy amount that is missing. For calculations, we can use an index element. Index elements don't have any own value, but derive their value from other elements in the model. I'm creating one for the missing energy here. We have 2 ways to build the index calculation. The simple one is using templates, but that only works if the calculation is really easy. I'm instead using the second option and build the calculation with our formula editor. Open up the editor here. To calculate the missing amount of energy, we can take the maximum amount of energy that fits in the element energy, which would be 2 megajoule, minus the amount of energy. That's all. Close up the editor, the formula is set up. Finally, let's add this calculated amount to the energy element each day of the simulation, using a flow, of course. We can use an element reference as a flow strength instead of hard-coding a value in the flow here. Switch to reference and select the index we just created. Now the flow will add the value of missing energy to the energy element each day. Let's simulate that. On day 1, we take 1 megajoule away. Now the energy element has 1 megajoule left. On day 2, the index calculates that 1 megajoule of energy is missing and adds it back using the flow. That way we won't ever run out of energy. At least in this model. In the real world, we might have to think about where our energy comes from and how sustainable these sources are, but that's a topic for another video. Now, you've got a good understanding of the basic building blocks of simcision flow models. Watch out for the next videos in the series where we will look at interventions and scenarios and how these can influence our simulations, analyzing your model, where you will get to know different tools to understand the relations in your model, and evaluating your simulations, where I show you the power of working with charts to really understand your simulations. See you next time. And don't forget, every model is wrong, but yours might be useful.